Okay, this is a velocity and speed video. We're going to be learning about velocity and speed. You should already know distance and displacement, those concepts, and also the concept of frame of reference for this to make sense to you. And velocity and speed, I think people tend to have a pretty good sense of how they work already. They're both how fast, and I'm going to put in and speed because I'm going to talk about both of them, and there are a lot of similarities, but a couple of key differences. So velocity and speed are both how fast. They're the rate at which position changes. Uh, Rates are changes with respect to time. The rate at which position changes means the change, and we write delta, that's a delta, change in position per unit time. And we'll talk about equations in a minute. The unit for both speed and velocity, the primary physics unit we talk about, is meters per second. Unit meters per second. Although very frequently you end up seeing miles per hour, just because here in the US we so often have examples that deal with miles per hour. So as long as you're really careful about your units, you measure your position in meters and your time in seconds, you can always come up with a velocity in meters per second. However, if you measure position in miles and your time in hours, and you're consistent throughout a problem, then that'll work out pretty well as well. So I wanted to start out one big difference in velocity and speed. Velocity is a vector. And that means that the direction strongly matters. It's how fast you're going and in what direction. And we've got a couple of different types. We'll talk about the instantaneous, how fast you're going right now, and the average. And those are both vectors if we're talking about velocity. Speed is a scalar. And speed does not concern itself with direction. So a velocity might be 4 meters per second north. Speed might just be 4 meters per second. It won't have a direction associated with it. And when we talked about velocities in the past, north is a direction, but also if we define a direction by giving a frame of reference, for example, if I say I'm going to call this direction positive, then we could just say 6 meters per second, and the fact that it's not negative indicates that we're talking about that direction to the left, whatever that happens to represent. Speed, a lot less pressure in that sense. We don't have to worry about direction. But in velocity, it's always useful to define a frame of reference. Okay, let me try to show you an example of the vector nature of velocity. And it's a good timely example in the sense that right now there's a hurricane bearing down on Florida. And if we look at a hurricane, I don't know how to draw a hurricane. Here's the eye, and then there's a mass. I'm not going to draw the arms of it, but let's say that's the hurricane. The hurricane's rotation ends up being like this. And its rotation, they say that the speed close to the eye wall is approximately 120 miles per hour. And I really don't like miles per hour, but I'm using this case because that's how everybody seems to talk about hurricanes. Well, that means this part here, it's a vector, and remember vectors we represent with straight lines. So let's just take that part of the hurricane there where the highest winds are. So if you're right here in the hurricane, you've got a vector of 120 miles an hour blowing that way. If you're over here, it's blowing that way. If you're over here, it's blowing that way, and if you're over here, it's blowing that way. And I really would like to draw those all the same length because they all represent 120 miles an hour. 120, I'll leave out the units. 120. So all the winds at that spot, that distance from the center of the hurricane, are going 120 miles an hour in the frame of reference of the hurricane. But the hurricane itself is traveling in this direction. And oh boy, I really apologize for not using the right sizes. But it's traveling this direction 12 miles an hour. That's clearly a different size. So relative to the ground, the hurricane is traveling 12 miles an hour. Relative to the hurricane, the winds are traveling 120 miles an hour in these directions. And I haven't drawn all of them, but there's essentially an infinite number of vectors I could draw on this circle, all tangent to the circle. So let's take this one right here. Okay, that wind is going in the same direction as the 12 mile an hour motion of the hurricane. So I'm going to draw it over here. And now I'm going to try to keep to scale. The hurricane is going 12 miles an hour. The wind in this part of the hurricane, just to the right of the eye, sort of east-northeast of the eye, is going 120 miles an hour in the same direction. So here's the wind, 120 miles an hour. And we know to add vectors, what we can do is add them tip to tail. Well, these ones happen to be in the same direction. It's kind of a trivial, I'm just going to slide this one over. And it's kind of a trivial case. But you have 120 miles an hour. 12 plus 120. If we draw the resultant from the beginning to the end, we find that the resultant is 120 plus 12. We can add them because they're in a straight line, same direction, 132 miles an hour. So winds here relative to the hurricane are 120 miles an hour, but relative to the ground, they're 12 plus 120 is 132 miles per hour. And we can do this with any of these. Obviously, the easy ones are the ones that are collinear. If we take this one, it's blowing back in the other direction. And let me come over here. And if we add, I'm going to do the tip to tail up here, 12 plus 120. 12 plus 120, they're in opposite directions. And so this ends up being a resultant from the beginning to the end, 108 miles per hour. So the big picture on this is these winds to somebody on the ground will appear to be 132 miles per hour. These winds to somebody on the ground will not appear to be as strong. They'll be 108 miles an hour. And we could do other things with this. This is perpendicular, so we actually can calculate size for it. I'm not going to do it here, but to construct that, there's 12. Then we take this and we put it tip to tail. And the resultant would be like this, and we could use the Pythagorean theorem. It's going to be the square root of 12 squared plus 120 squared. So that's an indication, that's an idea of this concept of vectors for velocity and how we can use those in the concept of other vectors. Another way that you see fairly frequently is an example like this, and I don't love these examples because it's not exactly correct to me, but we'll use it because you definitely can see this in an example. You have a plane flying north. And here's your plane. Whoa, that's a terrible wing. And here's this plane, and it's flying north at 100, we'll say 100 meters per second. Pretty fast. And you have a crosswind, and the crosswind is, let's say, 10 meters per second. And that's the wind. So the wind, assuming the wind's been acting on that plane for a long time, and we don't have air resistance back in the other direction, theoretically this 10 meter per second wind will push the plane to the right. I'm sorry, if this is north, to the east. at 10 meters per second. So to figure out how the plane will behave, you'll take the 100 meters per second and the 10 meters per second, and to find the resultant, we go from the beginning to the end, and the resultant is going to be the square root of 100 squared plus 10 squared. And so that's going to end up being the square root of there's 4 zeros there, 2 zeros there, the square root of 10,100 meters per second. It's going to be a little bit over 100 meters per second when you take that square root. But the indication, first of all, there will be a direction over here, and I'm not going to go through the whole, we've done vectors. This direction is going to be the tangent of 10 over 100. But once again, I just wanted to give you in this video an idea of what the definition of velocity and speed are, and how the vector nature of velocity is used to solve problems.